Okay, hello and welcome back. Today I'm going to be covering the squeeze theorem for limits. Here we go. So take a look at the um, following graph. Here on top we have g of x, and we have f of x, and we have h of x. Now, locally at this point, x naught, right? You would agree that locally at x naught, these functions all converge. But more importantly, take a look here and you'll see that h of x is going to be the bottom function, so it's less than or equal to f of x, which is the middle function, which is less than or equal to g of x, which is the top function. So if this is true and the limit, as x approaches x naught for g of x, so this limit right here is the same for both g of x and h of x. Well, this f of x is being funneled here. It's being squeezed. This theorem has a lot of names. Squeeze theorem, sandwich theorem, pinching theorem. I've heard that. All of these are, names that could be used, but it's basically showing that this function is being squeezed between these two functions. So, of course, its limit is also going to be squeezed between the two, and it's just going to be out. So the theorem's statement is that if h of x is less than or equal to f of x, which is less than or equal to g of x, and the limit as x approaches x naught of g of x is equal to the limit as x approaches x naught of h of x minus L, which is a real number, then the limit as x approaches x naught of f of x is equal to L. So the proof is actually rather simple. You're just going to say, starting off, by hypothesis, we know, well, what do we know? Well, we know that the absolute value of h of x minus L, of course, has to be less than epsilon locally at x naught. So we can say locally at x naught, this is true, and for g of x minus L, this is less than epsilon. And now this is true if and only if we know this is what's known as the conjunctive inequality, that we're going to actually split it into, if you remember what the limit was, how we're going to use the interval form, L minus epsilon, which is less than h of x, which is less than L plus epsilon, and L minus epsilon is less than g of x, which is less than L plus epsilon. And this implies, well, what does it imply? Well, it implies that we're going to be looking at L minus epsilon, which is less than h of x. This h of x less than or equal to f of x, which is less than or equal to g of x, which is less than L plus epsilon. So notice how the squeezing of f between h and x also puts the squeezing of f's limit. So L minus epsilon is less than f of x, is less than L plus epsilon locally at x naught. So this is true locally at x naught. And thus we can say, what can we say? Well, we can say that since this is true, we have locally at x naught, the absolute value of f of x minus L is less than epsilon, which actually just means that the limit is equal to that by our limit definition. So we're done. We're done with our proof. So how can we use this? Well, we're going to talk about another pretty important theorem. So how can we use the squeeze theorem? So we're going to be looking at some special trigonometric limits that the College Board loves to give. So we already did standard trigonometric limits, and that's fine. But what are some using the squeeze theorem? So first we're going to have a lemma that we need to prove. So this is a very interesting lemma, but it basically says that locally at 0, 1 is less than or equal to sine of x over x, which is less than or equal to cosine of x. The lemma is very easy to prove, arguably, but I'll show off one proof right here. So you're gonna have to start off by first making, the unit circle, right? We're talking about this. This is one way you might think about it, right? So we're gonna put this unit circle here. And now what can we say? Well, we can say essentially that this point right here, we're gonna create this line. This line, we're gonna create this triangle. We're gonna make this triangle. We are going to go down here. We're going to go down here. And we're going to copy the construction on this side. And basically, right here, I think it'll be easier. This green length highlighted, well, it's a bit big actually, but the green length highlighted is going to be equal to cosine of x, whereas the blue length that I'm going to highlight is sine of x. And we know, of course, that this purple length is sine over cosine because it's tangent, right? So what can we conclude? Well, we can conclude that by looking at the area and by calling this point Px, O, and A, right? And we can flip it on the other triangle to mean the same thing. So first, we're going to take case 1, which is for x being between 0 and pi over 2. So what does this mean? Well, this basically means that the area of what triangle are we looking at? Triangle OPXA is going to be less than or equal to the area of sector. What sector are we talking about? OPXA still, which is less than or equal to the area of the big triangle. Triangle OQX, which we're going to call this QX, and I should say that this is going to be our A, which is 1, 0, AQX, and that is our area. So this is for case 1. So if we express all the areas out, we're going to get that 1/2 times 1 times sine of x is less than or equal to 1/2 times 1 times sine of x, so less than or equal to sine of x over cosine of x. And this is true if and only if. Okay, so we're just going to get, by doing some algebra, first we're going to simplify this out and then take the reciprocal. We're going to get our lemma, which is that 1 is less than or equal to sine of x over x, which is less than or equal to cosine of x. And case 2 is very similar. It's just the opposite, so I'm going to omit that. We're just going to say that we've proven it. You should know case 2, but I'll leave that to you as an exercise because it's the same exact idea. Moving on to the actual theorem we want to talk about. Here is where we come in. Theorem, and we're going to call this a theorem because it is so big. You will see this on the AP exam most likely. So the limit as x approaches 0 of sine of x over x equal to 1. So one way of doing this would be, you'll learn eventually, you can use L'Hopital's rule. But this is the common way that you will first learn it. So here we're going to write proof for the theorem. So we know that the limit as x approaches x naught of 1 is equal to 1, which is equal to the limit as x approaches x naught of cosine of x. Agree? So this is true, and the reason why this is true is I forgot to write. This x naught that we're talking about is actually 0, right? So at 0, this is true. And what else can we say? Well, we know from our lemma that locally at 0, this inequality holds true. So this means that by the squeeze theorem, what do we get? Well, we get the result that we were looking for, because we just can figure out that since this function in the middle is being squeezed between these two, which have the same limit, the limit as x approaches 0 of sine of x over x must be equal to 1. The reason why this is so important is because if you won't get a problem exactly like this, but you might get a problem that says, okay, evaluate, I don't know, the limit as x approaches 0 of sine of 4x over x, let's say. How would you do this? Well, I'll give you just an example. This is a very basic example. We can go more in depth later. We want to write 4 times the limit as x approaches 0, so we're factoring out a 4 sine of. But remember, for multiplying by 4, we have to divide by 4. And this is equal to 4 times the limit. You would agree that the limit as x approaches, 4x approaches 0, right? Because if x is approaching 0, then of course 4x is also approaching 0, which we can be like our u, right? You may sometimes see this be substituted as like a u over 4x. And this is by our theorem that we just proved by the theorem. This is just equal to 4 times 1, so we're going to get 4. And this is a very interesting result to see, but it's actually really interesting because it shows how we can have a seemingly very difficult problem, 0 over 0, nothing easy to do, no factoring. We can take it, we can sort of just remove it completely, and this is going to be the setup for a lot of problems indirectly, mainly. So thanks for watching.